Okay, so we did the characteristic polynomial for a second order difference equation. One more time, that epsilon t is what type of noise?
White noise.
White noise. So we are actually modeling this noise, which belongs to the actual time series, but now epsilon t is white noise. We move the terms to the other side. We use the lag operator to get the characteristic polynomial, correct? That's where we left. Okay.
Why is text?
Correct. Since L is just an operator, we don't want to just have an operator. We should rather call it using a letter so that we can do algebra. So typical letter that we use is Z. We can also use lambda, but I'm going to reserve lambda for later. So 1 minus P1 Z minus P2 Z squared is equal to epsilon naught, excuse me, epsilon sub t. Now, we're going to model this in the sense this particular difference equation will be modeled properly if that term is 0, correct? If there is no noise, then we have successfully modeled the relationship between xt and xt minus 1, xt minus 2. Do you agree? But unfortunately, in practice, it's always there. Right? But it is a good thing. We are going to make use of that epsilon t to model, because it is a stochastic process. So, under the assumption that the right-hand side is 0, that's what we would have. What does it look like? You should know this. It's a polynomial quadratic equation. If we can't say it directly, if you rewrote it, minus P2 Z squared minus P1 Z plus 1 equals 0. Right? Ax squared plus bx plus c. So we are going to use this later on in what we call an AR2 model. And if we understand the second order difference equation right now pretty well, excuse me, when we get to that AR2 model, everything will be easy. So I'm going to show you a couple of ways in which we can find phi1 and phi2. Since that is a quadratic polynomial, it is going to have how many roots? 2. And how do we find the roots?
Quadratic formula.
Okay, minus b minus of minus phi1 plus or minus square root b squared minus 4 times a times c divided by 2 times minus v2. And that would give us phi1 plus or minus square root of phi1 squared, negative times negative for phi2. B squared minus 4 times C. Okay, divided by 2 times minus phi2. So we have the solution to that equation. So we have two possible roots, do we agree?
Yep.
One would be phi1 plus square root of phi1 squared plus 4 phi2 divided by minus 2 phi2. The other root would be phi1 minus square root of phi1 squared plus 4 phi2 divided by minus 2 phi2. Note, I'm using Z1, Z2 to differentiate between the two roots of the quadratic equation. Now, if we had a third degree, third order difference equation, we will have 3 roots. Fourth order, 4 roots, and so forth. I'll just generalize it to a third order when we get to, once I do third order, I will generalize it to a fifth order. It might look very complicated, but you know, if you understand the process, it's very easy. Are we clear with this? This part, phi1 squared plus 4 phi2 has a name.
Chili.
What?
I just give it a name, chili.
Honey.
Place of chili at first.
What's the proper name of jelly?
Joseph.
I don't like that thing. Discriminant, right? That's called the discriminant of the quadratic equation. So it is possible for that particular term to become negative.
Which case we can.
Right? Yes or no? That could become negative. If it became negative, what would that tell us? The solution will be
Irrational.
rational.
Yes, but.
What is square root of negative 1?
Oh, wait, square root, shit, sorry. What is it, square?
I. So it is complex, or it will be complex.
That's what I was looking for.
If the roots are complex, we know the roots are conjugates of each other. So, what do we mean by conjugates?
You have a plus and a minus. Like if you have 1 plus I, you have 1 minus I.
Exactly. So that is, you will have one root to be a plus ib, another root would be a minus ib. That is the nice thing about, you know, complex roots, because they always happen in conjugate paths. So what we're going to do is quite important, because when we go to AR2 models, when complex roots do happen, we need to find something called thetas to face. So we need to understand how to represent a complex number using exponentials. Does that look familiar? Differential equations.
What is that thing? Yeah.
Well, I think from differential equations is like the e to the t, and then the other stuff.
So that is a representation for a complex number in terms of, in a polar form. That simply means r multiplied by e raised I theta is cosine theta plus I sine theta. And if theta becomes negative, I'll have cosine theta minus I sine theta. No, I'm associating Z1, Z2, which we've used there over here. If I equate them to each other, I'll have A plus IB equals R times cosine theta plus I multiplied by R times sine theta. Distributing the R, and that's what I'll get. Good.
Maybe I think the same thing would be a minus IB.
Yeah, but if A minus IB, that would be minus, and that would be minus, right? So we don't need that because I want to find A and B in terms of R and theta. By direct comparison, what is the value of A?
R cosine theta.
By direct comparison, I mean, I'm going to equate that part to that part, that part to that part, right? So I would end up having A to be equal to R cosine theta, B to be equal to R sine theta. Look me so far. Going to divide B by A. So B over A would be equal to R sine theta divided by R cosine theta. What would happen to the elements? cancel. What is sine theta divided by cosine theta?
Tangent.
Tangent theta. Which would imply theta is equal to. I want to solve for theta.
Inverse tangent.
Inverse tangent, so you'd have tangent inverse B over A. I don't want to make the connection to this, but the model gets, we will save that when we get to AR2. So that formula for theta is tangent inverse B over A. But do keep in mind, they are related to those, right? Because those two play a part here, so because those are the two roots. So the value of A will contain phi1 and phi2. So we can plug in the values and we can find the value of theta. Good so far. Gonna erase this side. We want to find R. So theta is what we call the phase, and phase is related to the frequency. We'll talk about that later. R is called the magnitude. How do we find the magnitude? Well, if I squared
So that they go to phase.
phase, which is related to frequency. So we're going to evaluate A squared plus B squared, which would simply mean R cosine theta squared plus R sine theta squared. Which will give us R squared cosine squared theta plus R squared sine squared theta. What do we have in common?
The R squared.
R squared. If I pull the R squared out, I would have cosine squared theta plus sine squared theta. What would that equal to?
Yeah.
Can't, they must be. It is one. So such a geometric identity, so that would be equal to 1. So R squared is simply A squared plus B squared. Which would mean R the square root of A squared plus B squared. Mind you, you can only use this if the roots are complex. If the roots aren't complex, we can just stick with the Z1 and Z2 that we had initially. So this comes into play when the series tends to have complex roots. The roots are quite important in time series. Later on, we will see whether if it lies inside the unit circle or outside the unit circle. So the roots speak a lot about the series. Good so far.
where we're still going on with the complex stuff.
That's that. So what we did is we had the characteristic polynomial, and we found the roots of the characteristic polynomial, and I took a special case where we would have complex roots. If we have complex roots, we have to find R, we have to find beta. Right? All you need to know is this formula.